So let's now get to problem number 5b3, and I will get back to the first problem later. It is a one-dimensional collision. I start out with object mass m1, and it has velocity v1, and it collides with mass m2, which has velocity v2. This is before the collision. And here we see the situation after the collision very schematically. m1, v1 prime, m2, v2 prime. All right, if there is no external force on the system, only internal, momentum is conserved. So the conservation of momentum, m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. That is equation number 1, conservation of momentum. Now, I could delete these bars since I'm dealing with a one-dimensional situation. Keeping in mind that if the velocity is in this direction, we would then, for instance, assign it a plus sign, but if the velocity is in this direction, it would then have a minus sign. So I can delete the bars, not forgetting that this is now my convention. So think of the bars as not being there. Now it is given, or I'm telling you that this is also an elastic collision, so you also have that the kinetic energy is conserved, 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. That is equation number 2. That is the conservation of kinetic energy, which only holds if this is an elastic collision. And this is the conservation of momentum, which in this 1D case, observing our sign convention, we can then even delete the bars. If I massage this a little further, and I will let you do that, we have little time today, so you will have to do some massaging of this, you can then show that v1 minus v2 equals v2 prime minus v1 prime. And that is quite remarkable. This is the relative velocity before the collision between the two objects, and this is the relative velocity after the collision between the two objects. And it's not so obvious that that would be the same. Of course, it's only true if kinetic energy is conserved. But what is not required that m1 is m2. That is not required. When you derive that, you will see that that is not a must. Let's take an example. For instance, I have m1 equals 5 kilograms, and I have m2 equals 22 kilograms. This object v1 magnitude 3, and this object v2 in the opposite direction, magnitude 6 meters per second. Now be very careful, think of our sign convention. v1 minus v2, this is now positive, 3 plus 3. v2 itself is negative, minus 6, so minus minus 6 becomes plus 6. So this is plus 9 meters per second. And this now also have to be v2 prime minus v1 prime, observing the same sign convention. And this, of course, is quite remarkable when you come to think about it. Now you may say, well, great, I know the difference in velocity, but what is now v2 prime and what is now v1 prime? Well, now you have to go back to your equation number 1 and equation number 2. If you know v1, and you know m1, and you know v2, and you know m2, then you have in principle two equations with two unknowns, and you should be able to solve for v1 prime and v2 prime. And it takes a little bit of hassling, a little bit of massaging, a little bit of algebra. That you can find in books, or you can work on it yourself. It would be a waste of your time if I used my precious 57 minutes right now. So I will give you the answer. If you do it correctly, you will find then that V1 prime equals M1 minus M2 divided by M1 plus M2 times V1 plus 2M2 divided by M1 plus M2 times V2, and then we have V2 prime equals 2M1 divided by M1 plus M2 times V1 plus M2 minus M1 divided by M1 plus M2 times V2. And you can check whether I did that correctly. If you change in the first equation the 1 to a 2 and the 2 to a 1, you obviously should get this equation because the problem is completely symmetric. So let's take this term, the 1 becomes a 2, the 1 becomes a 2, the 2 becomes a 1, and indeed that looks good. This 2 becomes a 1 here, so I think we are great. This V1 is V2, this V2 is V1. So this looks good. Remember, this is only true if it is elastic, and remember that a positive sign means going to the right for the velocity, and a negative sign means going to the left. Now let's take a very special case. Let's take the case that M1 equals M2. Here is M1 with velocity V1, and here is M2 with velocity V2. And if you now take M1 equals M2, this is gone, and this is gone, this is 1, and this is 1, what do you find to your great surprise? That V1 prime equals V2, and V2 prime equals V1. And what does this mean? That after the collision, the velocity of 1 is now the velocity of 2, and the velocity of 2 is now the velocity of 1. And that is not so obvious. So they exchange the velocity. By no means intuitively so obvious. So if we take a very special case that V2 equals 0, it would follow then from what I just told you that V1 prime would be 0, they exchange, and that V2 prime would be V1. Now I would like to demonstrate this to you, and the best way I could do that is to have two pucks of equal mass, and this one bangs into this one will be standing still. There has to be no friction, and I could show you then that after the impact that this one gets this velocity and this one stands still. But I don't have a frictionless horizontal table, so I can't do that. You may say, well, do it with marbles. Well, if I do it with marbles, there is another problem. I can take two marbles of equal mass, but when I do this collision process on my pad, then they begin to roll. And rolling adds a complication that we have not at all discussed. And that is very special. And so we can't do it with rolling marbles. That's a little tricky. And if you slide the marbles, then there is friction. And if there is friction, there's external forces. So let's not do it with marbles either. I will do it with a pendulum. I have here a pendulum, and I have here a pendulum, equal length and equal mass. And I will swing this one towards this one. You will say, well, there are external forces, there's gravity, which is very true. There is a gravitational force here, mg, and this accelerates this object. So clearly, if there's an external force, how can possibly momentum be conserved? Well, at the moment that they collide, in the x direction, there is no external force. They collide, there are internal forces, action equals minus reaction, but that's okay. There are no external forces in the x direction. So as they collide in this direction, I have in the x direction, in the horizontal direction, an ideal situation. Kinetic energy is conserved because these metal balls are very flexible, they bounce back very nicely, and in addition, I have no external force, so momentum is conserved. And so when this object hits this one should stand still, and this one should pick up this speed. And this is something that I want you to see. I will do it with this famous device, which is called Newton's Cradle. You see here the two pendulums, equal mass. We will show it to you from above. That's easier, because I can also zero in then, and then you see it better. In fact, when I zero in, you don't even see the vertical motion, you only see the horizontal motion, which makes it even more convincing. So I move this one out, and at the moment of impact, I have kinetic energy conserved, and I have momentum conserved in the x direction. There we go. So watch as this one hits, that this one will stand still, and this one will pick up that speed. Are you ready? There we go. You see? It stands still. And I go back, and it stands still. And of course, if you do this, then you get this alternation, which you have seen, no doubt, many times. A great toy. Oh, can I have the overhead? Because I want to be able to adjust the screen. A great toy, and it makes this point very convincing. So let's now take a situation that M1 is not M2. But let's, for simplicity, still take V2 equals 0. So our equations become a little simple. It's the same equation that I wrote before, but I substitute V2 equals 0. So this is V1, and V2 prime equals 2M1 divided by M1 plus M2 times V1. Same equations as before, but I substitute V2 equals 0. Now let's just assume that V1 is in this direction, which we have called positive. And of course this holds only if kinetic energy is conserved, because that's the way we derive them. And it holds only if there is no external force on the system, so that momentum is also conserved. That's very important. And now, notice that V1 prime has three options. It can be larger than 0 if M1 is larger than M2. It can be equal 0 if 1 equals M2. We saw that before, that's not new. But it can also be smaller than 0 if M1 is smaller than M2. And this is intuitively pleasing, because what it means is, if a small low mass ball, like a ping pong ball, collides with a baseball, or with a billiard ball, maybe better example, then it can bounce back. It's intuitively pleasing, and you see that if M1 is smaller than M2, it will bounce back, it will go in this direction. However, V2 prime is always larger than 0. Notice no matter how you choose here, M1, M2, or V1, if V1 is in the positive direction, then V2 prime is also in the positive direction. And that is also very intuitive. Because if I have here an object and I hit it, obviously it must go in this direction. It would be absurd if I hit this object that it would go back. That would be absurd. So it's completely consistent with what we find here. V1 prime, you have three possibilities, but V2 prime always goes into the direction of V1, and that is exactly what you would expect. Now we'll take an extreme case that M2 goes to infinity, so we have a wall. Now obviously V2 is 0, the wall is not moving. Now let's assume the wall is not moving. If the wall were moving, the kinetic energy of the wall would be infinitely large, so that would be a bit of a problem, so V2 better be 0. And now I find if I collide an object with m1, which goes with velocity v1 against the wall, I find that v1 prime equals minus v1, and I find that v2 prime equals 0. Kinetic energy is conserved, and momentum is conserved. This is quite obvious, you would say. This is the wall. An object comes in here with a certain velocity, and it bounces back with exactly the same speed, but it reverses its velocity. Yes, this is very intuitive, but I want you to think about something. The kinetic energy is all in here, is not in the wall. The kinetic energy of the wall before and after equals 0. The kinetic energy here is 1/2 m1 v1 squared, and it is also 1/2 m1 v1 squared when it bounces back, because look. So that's fine. But let's now look at the situation of the momentum, and I'll give you some numbers. It's easier to deal with. M1, let's say, is 1 kilogram. That's the ball that bounces off the wall. It comes in with 5 meters per second, and it bounces back with 5 meters per second. In other words, P1 has decreased by 10 kilogram meters per second. It's first in the positive direction, and now it's in the negative direction, so it has decreased by 10. However, I've stated that momentum must be conserved. How can it be? Momentum is changing. Is it perhaps true that the momentum of the wall is also changing, so that the net momentum wall plus the ball is 0? It better be, but it's kind of puzzling, isn't it? Because the wall had infinite mass and it has no speed, no velocity before the impact and after the impact. You think about that, and it's very important that you get the answer to that, because it's very fundamental. The conservation of momentum must hold. So yes, indeed, the wall must have changed its momentum, in spite of the fact that it never moved. Is that cute? Think about it.